Hey everyone, so today I will be talking about mm, angular momentum, but angular momentum in quantum mechanics actually. Yeah, so basically quantum mechanics today. So this thing, quantum mechanics, is honestly pretty weird. I mean, it's so weird that I just can't imagine it. Like I just can't, even picture things about it. It's weird. It's very weird thing. It's very weird. Like uh, like how do I imagine physics? Generally, I just try to picture things happening in my mind. That's how what imagining means for me, and most of the people I hope. And so if I'm standing here, uh, I can see stars above me in the sky. I know what they are doing. They are also moving. I am moving. I can tell where they are going if I calculate, do the math, measure their distances from a telescope. I know that I am also revolving around the sun. I just know too many things from the world around I see me. Even if I can't, even if I'm not capable of calculating, I know there are smart people around there who do. There is a lot of data, a lot of information about these things. How fast the sun moves, how fast our planet Earth moves, with respect to something, of course. We just know moments, motions, everything. We just can predict things. If something happens initially, what will happen next in the world we can see around us, but this only happens in the world which we can see. In quantum mechanics and quantum mechanics quantum mechanics is the world which we cannot see. We just can't see, unfortunately. We can only observe by some tools. We can never see. Uh, we can just see the after effects. We have, like, we cannot see an electron. We cannot see a proton, and this proton is made up of quarks, and we can't even see this up down quarks. All these quarks, we can't just see them. We honestly I don't know if I should say, but I don't even know if they exist. We just have too much of proof that they exist, so they must exist. This guy called Max Planck, did an experiment. He found there is some kind of negative stuff coming out uh, from objects, and that negative stuff he called electrons. Uh, we just have too much of experiments which say, yeah, these things should exist, but we can't ever see them individually from our eyes. We can't just see them like we see other objects. Quantum mechanics is something which we cannot observe directly. We can only see the effects and tell what must have happened or what will happen later, and we are never sure what exactly will happen later. We just tell what may happen. That's quantum mechanics for you. At least that's what I think, and I may be wrong in a lot of ways, but this is what there is for now. And so how should I say, angular momentum I want to talk. I will talk. So basically, let me just do a little warm up. So let's say you have a center, and this is your proton, and this is your positive charge, and an electron is moving around it. So the problem is, we found in quantum mechanics that electron can't move around it like this in a circular way. It is not possible. So we just know that electron is somewhere there around this proton. It must be there, it is somewhere there, but we just don't know what exactly does this electron does, how exactly this thing moves. We don't know, we just know it's somewhere there. We know where it may be, chances of it being there and all that. But for now, let us assume that let us for now assume that this thing is revolving in some way. Let us say that this thing is revolving. And what is the problem if this is revolving? So the thing is, we, as far, I am very bad in this, but we took a test tube. We took a test tube, um, and there was a lot of gas in this. We filled this with hydrogen gas. So there was a lot of gas inside. This hydrogen gas in a glass tube. So this was filled with hydrogen gas, and what we did is we attached this to a battery, a very powerful battery, and we are free to, let's say, change the voltage. Like, more we increase the voltage, more will be the current going through this wires, these wires, and so if the current is strong enough, if the current is very strong, like if this battery provides very high power, then because of this battery, the gas inside uh, gets energy. It cannot stop this energy from coming. It just increases in a very high degree. And because of this, what happens is, so all of these individually inside are atoms, right? So these are atoms inside every individual of them. These are hydrogen atoms, and hydrogen, in theory, that's what we believe, it has one proton, a positive charge, and one electron revolving around in some way. One electron revolving around. That's what we think. So one electron revolving around. Now the thing is, um, when you give, so basically, when I increase the voltage, this means electric field is in this now. There is a high electric field. Electric field is something which makes charges move, uh, which gives energy to the charges. An electron is a charge, so a charge particle. So what happens is, this thing will get energy once I apply an electric field, strong electric field, and so basically I somehow made it to move faster. That's what I did. Somehow I did. There are ways, I suppose, and I used some way to make it move fast, pretty fast. And when I did that, what will happen? That is the question. Will it make a bigger circular orbit, a bigger circular trajectory, or will it just bounce off and go out far away, or the completely impossible scenario, will it go inside? Something what would happen? And it turns out that one scientist, his name is Niels Bohr, he said that what made him do that, I really don't know. I suck in quantum mechanics. Okay, I suck the most in quantum mechanics. I don't think I can ever understand quantum mechanics. I am shit when it comes to quantum mechanics. Everything I try to do, it just falls apart. I don't know quantum mechanics, but I still want to talk about it because this is my channel. So this is an electron, and this is an electron. So if If really this electron is going around this proton, that guy said, Niels Bohr said, okay, maybe it must have some angular momentum. Let us say it has some angular momentum, and we will call it uh, let's say, let me draw a line. I will write this side of the line. We will say that it has some angular momentum. So in math we write angular momentum, we use capital the letter P. Okay, we use L, yeah, P is for linear momentum. So it must have some angular momentum, which will be this multiplication. So this quantity here is the mass of the electron, this is the speed of the electron, and this is the uh, what should I say, this is the distance from the center, from this proton. This is the angular momentum. So what this guy said is, okay, if this thing has angular momentum, if this thing has angular momentum, it cannot have angular momentum of all possible values. So if I this is my real axis, so real line from positive real line, so this real line has all the numbers, right, inside everything you have. It's telling everything is not possible, every value of angular momentum is not possible. There are only some allowed values of angular momentum, allowed values on this real line which are possible. So, and each value will be in terms of h cut. This is a number, by the way, this is just some number. 1 h cut, 2 h cut, 3 h cut, h cut, h bar, h cross. I don't know how many names does this thing have for h cut, whatever. So h cut, this is approximately equal to 10 power minus 34 joule seconds. This is in units of angular momentum. So it is measured in units of angular momentum. That's a good thing. Quantity. So he said, whatever the angular momentum is, I don't care. It should be 1 h cut, 2 h cut. So this is n. This can be 1, 2, 3, 4, 0 minus no angular momentum. It should be like this. And then so angular momentum in physics we say quantized. Angular momentum is quantized. This guy assumed it. What will happen if this thing is quantized? His question was. So he's like, okay, let us see what we'll assume that. So this was all he did. He said, okay, let us see. So how is this any special? I don't know. Let us just keep doing and see what happens. So if angular momentum is quantized, this thing, so what will happen to the particle? Let us see. So this particle is under influence of this force of attraction because of the positive charge, and so, and that force of attraction is actually of this much size. So if I am not wrong, it is E square by K E square, K times E square by distance square. So distance from the center. So distance is, let me write it down. K is 1 by 4 pi epsilon naught. This is some number. So is equal to, and this will be balanced out. This will be balanced out by uh, the centripetal force of the electron. I mean, so basically what happens is, when something is rotating, it tries to I don't know, for some reason escape in opposite to the opposite in opposite direction of its circle motion, and this escaping uh, movement is getting balanced out by this force which this proton is producing, and this thing is perfectly balanced out such that it neither goes this way nor goes this way, and it just revolves in the circular path. It just gets balanced out, and that quantity, that how much amount is this much. We write like this. Okay, fine. So what? So let us do the math and see just what we get. We just play. So as you can see, I can just cancel this and this. Like there are 2 hours math. I'm just doing math, and so I can write. Let's see what we do. I am just playing. It may take a lot of steps. I just seeing what all is possible. So okay, so this is certainly a possibility, right? I can do this. Then what more can we do? So, what more can we do? Let us see. Mm, so, we know that. Let us see what more can we do. I just. There are many ways, so I don't know which one should I use, which pleases me, which I like. Uh, so, look here. I think I will just do this one. So this one might be better. So I can separate this thing like this, right? MVR times V. Right, just math. So K E square is so what is MVR? We know that this assumption we don't know if it is or not. We just assume maybe. So it's NH cut times V. And what am I seeing? What am I saying? If I do more math, I see that this is the case. So this is the possible speed. So what more is possible now? So now we will let's see what we can do. So look at this number. I mean, this number, I know this cannot be changed. This is what it is. This also cannot be changed, and this is also a number. Now the thing is, if I just take this number as some bigger number, so I can write this as something like this, and this is can only be 1 2 3 4 and so on. Zero doesn't make sense because it just has no point, but you can take zero fine infinite speed. So speed cannot be anything. Speed can only be so let me use calculator and see what all values I get. So this is a calculator called Desmos. So let me put everything here. So okay, so what happened? Okay, so I have to let me rotate the screen. So here we go. So I will use Q for charge value here because E here is reserved for Euler's number. So the charge of an electron is about this much. This is the charge of an electron, and then and then we have mass of electron, which is this much. I hope I'm not writing wrong. And then K. That K is somewhere about 9 times 10 power 9. So yeah, this is all there is. And so that thing, that capital C we wrote, it will be somewhat like this, right? So it will be, what was it again? Oh, H. How can I forget H? Let me define H. H cut, I will just write H cut as H. Let me be more precise. So yeah, this is about this. I hope my numbers may be here and there a little, but it won't change much. I hope so. It won't be that much of a dramatic difference. So what was C again? What did we found? K Q square by H. So Okay, k uh, q square by h. So look at that speed, man. This speed is insane. If I plot this, let me plot this, c divided by n. Okay, c divided by let me just write x. If I plot this, you can see this it's come on, yeah, here it is. So when it is 1, when the value is 1, when the value is 1, let me put 1, it's somewhere here. The speed here is like oh my god, that's like 75% speed of light, which I feel is bullshit, but here it is. And then the other speed is some 30% the speed of light, 33 or something, 33, 35, and it just keeps on. These are the only possible speeds the electron can have if we just think it that way. But this is not I think what many people say. So what they do is they don't even care about speed for some reason. What they say is, so you got this formula, right? Now what you do is take this, and can you see v here? So let me write, we know that n h cut is m v r, right? So this v, replace this v with here, with the quantity here. So n h cut is equal to m, that constant you got, by n times r. So you get n square h cut is equal to mc r, and this r which depends on your which depends on this number n, is equal to uh, which is equal to n square h cut by mc. Yep, that's what it's equal to, n square h cut by mc. Why do we care about r though? What is so special about r? First of all, let us plot this n square h cut by mc. So let me write this, n square h cut by m c. Okay, some number we got, and this depends on n, right? So let me write what is n here. N hasn't been given any value, so how am I sure? So yeah, n is here, n has been given a value, n. So let's say we make n an integer. It can vary from 1 to 10. So here we have different values of n, and you just put it down here. So you can see for different n you get different values. And why is this important? So there is this concept of energy of electron in hydrogen atom, and we write it something like this: energy of electron is given something like this: e minus k e by rn. And if you just put everything you have calculated before, what you get is minus ke, it is already the way it is, and just invert this thing because it's below. So you write m c by mc by n square h cut. So what do we get? We get minus k e m c by h cut into 1 by n square, and let us see what more we can do. If we can simplify things more, k will be k, e will be e, m will be m, h cut will be h cut, and c, as you know, c we had definition k e square by h cut. We will let us write that k e square by h cut, right? Okay, sorry, k e square by h cut. into 1 by n square. K e square by h cut into 1 by n square, and let us just write all these numbers. It is minus k square e cube m, I am not messing anything up, I suppose, h cut square into 1 by n square. And let us just plug all these numbers in the calculator and see what we get. I know the result, so I can, if it matches, good for me, or else I have to recheck the math. K square, then there is charge, right? Q square, k square, q square, q cube, right? Charge cube, yeah, charge cube, k square charge cube by this square times mass times mass times the mass. Let me multiply the mass, and I just don't I have to divide this by q. There is something called electron volts, and this is not what I wanted. This means I officially messed up in the math, I suppose. So let's see where I messed up and fix it. So let me see. So I think this is correct. There is no mistake in this one, and this is also correct. I can't change this. Minus k e, and then I just wrote everything right. K e m by, yeah, this is also correct. This thing I substituted, which is k e square by n h cut, k e square by n h cut, and then there was h cut square, k e cube m, k square e cube m, and h cut square, and k square e cube m by h cut square, k square e cube m by h cut, and oh man, I don't know. I don't like, just stopping the video, doing behind the screen. I just want to do it on the screen. It doesn't matter how long it takes. So let me see, where did I go wrong, or did I go wrong? Um, come on, where is the mistake? What if I add another q here? Okay, I think I got my mistake. I need the energy, so there is supposed to be a e square here, because there are two charges. I see there will be another e square here, another e square, so there will be e power 4 here. Okay, not bad, e power 4 here. So yep, I think I'm going good now. 4, I'm still a little close. I have still got a mistake, and now what the mistake is now, I don't know what the mistake is now. What more am I forgetting? How can I mess up so much? But here I am. So here, this is good, this is good, this is good, and yeah, also let me write this here, mistake. And then there is okay, so why would there be a yeah, also I remember I never talked about how this number h cut came in the first place. There is some, like, I should say, there is a guy called Max Planck. He should be regarded as father of quantum mechanics. Like, he is the one who is responsible for starting it all, I think. He got this number h cut, by the way. And so I think I can cheat now. I will just go to internet. Niels Bohr postulate. So that is what we are using. This is what we are, the third one. Okay, this guy had three postulates, I mean three statements, but we are we were interested in the third one the most part. Okay, so we'll just stick with the third one, and let's see what more mistake I have done. Okay, I have to also now skip a little. I mean, I have to pause this thing behind the scene and come back, or else I don't want this video to be like a day long. Okay, one thing I found out, I am not wrong. Okay, there is nothing wrong here. That's a good thing. Good. Okay, so this thing I found is not exactly energy. I mean, it is energy, but not the total energy. This is the potential energy. This is the potential energy of this electron. So this number, I will call this, let's say, let me call this A, capital A, or mm, A, B, C, D, E, F, G, H. I don't know. I want to use capital G pi n square. This is my potential energy. And so we also know that I know that there is total energy. This energy of anything, energy is stored in form of both kinetic and potential energy. So I need kinetic energy and potential energy. So I found out the kinetic energy. Let me see what is the potential energy. Potential energy, I mean, I know the potential energy, I don't know the kinetic energy. So for kinetic energy, we use this formula, this old formula, and so it will be half times m times, so velocity, our old friend velocity, we know what possible values it can have. Here it is, k square e square by n square h cut. K square e square by n, what am I doing, k e square by n h cut, k e square by n h cut, k e square by n h cut whole square. So this will be half of m k square e power 4 by n square h cut power 4, which k square e power 4 m h cut 4, k square e power 4. So this is again nothing but my alphabet G. So my kinetic energy is G by 2n square. So yeah, I'm ready. So I will have so let me use a rule sheet for a reference, or else I am just gonna, yeah, this is good. I think this is better. So now I can be in more order. Okay, I have messed up a lot, but let's go. So the total energy is kinetic energy plus potential energy, and my kinetic energy happens to be G by 2n square, right? Yeah, and my potential energy was G by n square, and so the doing the math, I get G by minus G by 2n square, minus G by 2n square. This is the total energy, and how much is this? We do the math, we know the capital G value, or do we? Let us write. So this was my capital G, right? So this is let me write properly. So this is my capital G. This is my capital G. This much joules, 4.33 in 10 power minus 18 joules. Oh yeah, G by 2. No, just let me just write this. So it is G is 4.33 10 power minus 18 joules. So I did so much to get this formula. I don't know at what cost, but something I did. I got this formula, and generally we write energy in terms of electron volts. So like from kg to pounds, like similar to how you do conversion between kg and pounds, centimeter and inch. We generally talk in terms of electron volts. So how many electron volts does this make? Just divide this by the charge and this number. So let me see how much will that be. So G by G divided by the charge, this much of electron volts, 27.06 electron volts. So this is equal to 27.06 electron volts. So the energy is equal to, so how much is this divided by 2? 13.5. I will just approximate 13.6. Okay, fine. So energy is minus 13.533 point by n square, and this is electron volts. 13.533 electron volts by n square. Well, the standard result is 13.56, but of course I wasn't precise. I mean, I have taken a lot of approximations, so this is how it is. So you can always bring a better number by inserting more correct values, more precise values. So okay, I did this, the energy. So you can see energy, total energy of electron and hydrogen atom cannot be everything. It has some possible values. Let us see what all possible values it has. So I will just remove these old graphs which are not needed anymore. So 13.66 I mean 533 divided by n square. Okay, so there are no graphs for us. No, we have graphs, and these are the graphs. So as you can see, the one of the possible energies minus 13.533 electron volt, and then the other possible energy is minus 3.833 electron volt, and so on. These are the only possible values of energy. So what this means is, I will tell, minus y minus. So this much of energy is needed if you want to completely get the electron out of your hydrogen atom. And what happens is, okay, we got this formula. So imagine there is this hydrogen atom in the center. Okay, and there is this electron here revolving, doing its own thing. So if I give so minus means the reason there is minus here is that much energy is getting needed to keep this electron inside this size, in confined in this much place. So if I somehow succeed in giving electron this much of energy, what this electron will do is it will just say tata bye bye and escape. And when it escapes, like before, it is not here, right? What happens is this electron gives this thing called light, gives out light of different frequencies. It gives radiation, and we remember I talked about this experiment. So what we did was, when we gave this energy, So the light came out, light of different frequencies came out, and we have one device, one very nice device. It's a miracle device. It is called a diffractor, a diffraction grating. It separates lights of different wavelengths. So when light passes through this, it gets separated in lights of different wavelengths. You can easily tell which light is which wavelength because of this separation. And we found out that which light of which wavelength is there. So what we found was, let me show you. There is this thing called hydrogen spectra. So what happened is, when you passed current through a hydrogen atom, I don't know, visible light came out. If it was some other light, I don't know how will be detected, but yeah, good thing this visible light came out. Like you can see, these all lights came out. Purple light, light purple light, light purple color, and then cyan color, and then red color. And we had to give a theory, give some kind of formula which will which matches with this result, which tells us that okay, if we do the math, if we put all the results um, in a formula, we will get these results perfectly. Whoever does that is a will be considered the smart guy. Niels Bohr did it. So yeah. So what was the wavelengths of those lights? Let us see. uh, Wavelengths. So it's coming. Okay, and it is slow. For some reason it is slow now. We have to wait. Let me skip the waiting part. Okay, we are back. So what all wavelength lights came? Please show me. I think it is there in the Wikipedia. Come on, Wikipedia, please. Here is the Wikipedia. mm, so I think this is the thing. So these are the different wavelengths which came, I think. So the first light which came was this 122 nanometer light, then 103 nanometer light, uh, 97 nanometer light, and so okay, so light which we can't see also came out, but the visible light was the one which we were able to. What is happening? Okay, I think I hope the video still continue to being recorded. So uh, okay, the video is still continuing to be recorded, I suppose. Yeah, so let us keep going. I need this picture, so I will take picture of this and paste it in the slate. So where is this? Here it is. uh, Let me just paste it here. Okay, so here it is, and we have those energy formulas. How much was that? Minus 13.6, minus 13 point, let me just write it as G, minus G by 2n square. Also remember, this is the energy. uh, so you have this different n values. Like imagine you have this hydrogen atom here We have to do a little more math. Fuck, we have to do more math. Shit, I don't like doing math, but damn. Okay, okay. So this is the first value, and then there is another one. There are different n values, because you can go further and further because you remember we had this formula for r. It can go further and further. So you have this first n value, then you have 2 value, and so on. This is not up to scale at all. This is very very bad sketch, but still you got it right. The more there n, it goes further. So the thing is, this formula is only for one. I mean, this formula is only for when it is at n, when it is at end state 1 2 3 and just completely goes outside. This is not of much use for us. I mean, we have to also find out what happens if it goes from one end to other end. So let's say this is for one end, like this was for one of the n values, and one of the shells, it is in one of the shells, and then it is in another shell, then it went to some other shell where this shell is bigger than the previous shell, then this is a minus g by 2m square. So we can write this as the difference is energy. The difference in energy is so minus g by 2 will be like the way it is, and just so it will be, which one should I subtract, which one will have more value? Of course, the closer you are, the more value you will have. Yeah, so here it is. So this will be the change in energy, and this is what we are supposed to be finding. If it goes from first shell to second shell, third shell to fourth shell, whatever, we can do it. So let me write this formula in Desmos as well. Minus g by 2, so g of n comma m, n comma m, okay, function, some energy function, h, I don't know, some energy function of, okay, I can't even use n and m, I think, anymore. I will just use capital N and capital M. Some function is equal to minus g by 2 1 by n square minus 1 by m square. Yeah, here we have a formula. So you can check for different values. Like example, let's say I transition from first state to second state. Oh, also let me write everything in electron volts. It will be more neat, more watchable. So yeah, look, when I go from first shell to second shell, I get this much of energy. Also, let me make everything positive. I mean, if you give me this much of energy, I will go from first shell to second shell, and you can keep doing that. So let us so this is good. So this will be the, also, if what it means is, if it goes from nth shell to m shell, like let me draw it. So let me so these are different circular orbit, right? Let's say this is one of the n and this is one of them. There are many other between them, but I don't care. My electron went from here to here, so I provided some energy, that is why it went from here to here. When it goes from here to here, what happens is, actually not going from, okay, I have to be more careful, damn. So when I provided energy, it went from here to here, it did nothing. Okay, when I provided energy, it went here to here, but while coming back, it will come back, it will eventually come back. While coming back, when it came back, what happens is, once it went and came back, then it will release light wave radiation. Only when coming back, while going, I provided the energy, so it went from here to here. Okay, so I hope listen carefully. Even if you don't, I don't care. When I provided energy, it went from n to m, but for some reason this electron doesn't want to stay here. It will go back to n, and when it goes back to n, after it goes back to n, in this journey, while it was in this journey, throughout this journey, once it completed this journey, it will release this radiation outside of different wavelength, and we can calculate it. How much that wavelength is, we have to find out. So how much that wavelength will be? So one more formula is there. uh, Wavelength of light, some other smart guy found out, is so basically energy of light uh, is uh, h this much. This is a relation between energy of light and its wavelength, and I will do more math. So it will be okay, here we have. And so the wavelength of light depends on the energy in this way. Okay, so let us see what happens. So this is what we got, and why is this important? Let me put that picture back. Let me put that picture back here. So you can see, when it goes from 1 to when it goes from 1 to 2, it will release a light of 1.22 nanometer. We will check if that is the case. So we will go back to the uh, formula. So this is the energy thing, right? Let me use it capital E now. Let me use it E. Okay, this is the shit, what am I doing? Go back. This is my energy function, so I will use capital E to represent it now. So my wavelength will be, so what was the formula? H cut c by 2 pi. H cut is simply h here, hc by 2 pi times 1 by e. E of course that uh, transition from one state to other. Did I mess up? Okay, I have to put things here as well. And comma. C is not defined. Okay, how did I not define it? What the hell? Here it is. C is defined now. W is also defined. Let me just write everything down. So look how, also I want this in nanometers. So am I doing it right? I think it is the other way around. I want this in nanometers, so I will just multiply it in 10 power 9. Yeah, everything will be nanometer now. So let us see how much will the wavelength be when it goes from first shell to the second shell. This much will be the wavelength. Okay, is this correct? I doubt now. Also negative sign because I want positive values. So did I mess up somewhere? Let me check. So yeah, when it goes from the first shell to the second, it releases, I mean not going, after going, while coming back it will release radiation of this much wavelength, and I think it's not matching with my formula. Okay, damn, everything should be okay. I have to again, this is not in, I have to write in SI units. Okay, electron volts. Yeah, so when it Okay, it is good now. It is in terms of ng. My capital G is also in SI units. Everything should be SI units now. Damn. So here I go. SI units, everywhere SI units. My calculations are the correct. H cut C by 2 pi math HC by lambda and H cut 2 pi. Okay, I messed up. I did the wrong math. Sorry for that. Happens. 2 pi should be on the top, and then 2 pi should be on the top again. Okay, I messed up in the math. Two pi H cut C. Noob mistake, so I have to just put it all here. So 2 pi will be here. Oh, we got it. You see, so when it goes from 1 to 2, it releases a light of 122 nanometer. So let's see, do more. What happens when it so I need just a calculator and this formula, and so you can see when it goes from 2 to 3, when it goes from 2 to 3, it releases a light, not 2 to going, while coming back from 3 to 2, it releases a light of wavelength 656 nanometer. Let's see, 3 and 2, right? Plus minus, forget about the plus minus. So it goes from 3 and comes to 2. You see, 661, which is close, it will always be close. It like plus 5 6 5 4 units, just forget it, it will always be close. That is the thing. Let us do for 486 when it goes when it comes back from how much this is. Okay, I have to label them. This is not enough, even though it's labeled. This is my 1, this is 1, this is 2, this is 3, and this is 4, and this is 5. Yeah, when it let's do for this. When it comes from 4 to 2, it is 486. So somewhere around 480 it will be. So let's see when it comes from 4 to 2. You see, it's always the case. 490, it's still always, it will always be close, because it's again in physics. uh, uh, just see about the closeness. If it is drastically changed like 10 times, 5 times, double, it is, if it is even double, or even half of the value is more than that, then that is a different case. Like even if there is a 50-40%, this is a error of like 1% or something, lesser than 1%, so I'm good with it. 490. So let us see what happens. So yeah, we are good, we are getting values which we want. And remember the purple light, I don't know. So I think it is there is something called Balmer series. So this is all the watchable light, like purple light, cyan light, green light, which we saw. So when you go from when the electron goes from 6 to 2, we call it transition though. When an electron makes transition from 6 to 2, you get 410 nanometer light. Let's see if it gets that. So 6 to 2, you see 413, that's very good, very close to 410. So yeah, this formula was given like 100 years ago, almost 100 years ago, by a guy called Niels Bohr, and it works. Not just hydrogen, we I think we are smart enough now, like we have enough formulas to actually tell for other gases. We just know that for every gas how much light comes out. Like we actually use this thing called uh, what was it, that uh, spectra, as identity card, ID card for every element. So let me spectra. So every element has its own color spectrum. So emission spectrum, color, we will just look at the emission spectrum. So the people who study things in space, who find out like how much of what is there in space, like what is an asteroid made of and all that, they use this idea. They just find out how much light is absorbed when they send light, how much of it doesn't come back, how much of it got absorbed, and they just tell, they very confidently tell that is that element which we uh, pass light through. So this is for some of them. Oxygen has these, hydrogen has these, nitrogen has this. These are called emission spectra. It is like an ID card of elements. Every element will have its unique emission spectra, very unique. Others can't have that. So this is a very cool picture. Now I want to download it. Yeah, so I think I can make it a wallpaper. This is too good. Yeah, so let me visit this. I want a HD pic. Okay, I will download it and let's. So yeah, here I go. Where is it? Download image. Yeah, so let us go back now. Okay, you have other pictures as well. Very nice pictures. You can see and get a better understanding. I don't know what this is. Oh, okay. This is the same thing. I will download this as well. I need more HD picture of this. So okay, I will skip this part. I'm downloading pictures and come back again. Okay, before going, I think okay, I can't do more. I guess for now. Before going, just watch this cool, whatever this is. Hmm. Is this? I don't know what this is. Click for full screen, but I'm already in full screen. Okay, no, I'm not in full screen. Damn, what is this? It's too beautiful. I will watch some other day because yeah, you can watch this from this website atomicspectra.net. Very nice website. Okay, so yeah, that's it. Uh, so why angular momentum? This idea of angular momentum in physics, in math, just in paper and pen, can explain things which we can verify, which we can find out using tools, using a microscope or a kind of this very important device called spectrometer. I am a theory guy, so I haven't used this. I don't think I have ever used this thing. So uh, but yeah, this spectrometer we used to find out. So that's it for now. So yeah, you if you made this far, thank you for watching. Bye.